Okay, that's
It's like can I bring like a sophomore? I have
so last time we practiced counting. Hopefully we start to get a feel for how we want to look at counting different situations. We'll be doing that while we're doing probability as well. Alright, settle down now, we're starting. But before we jump into probabilities, some more preliminaries here. One, I want to introduce a definition. A, B are sets. We say A and B are disjoint. They're not joined by anything if their intersection is empty. They don't have anything in common, which means if you're drawing a Venn diagram with A and B, they would be separate circles. They will be disjoint. They won't have anything in common. So just want to define that word because I'm going to be using it soon. I also want to mention one thing I want to mention here is the use of tables and tree diagrams. That might come in handy. To illustrate, let's revisit that example. Points. How many outcomes? Now, we know one way to look at this is the multiplication rule. Basically, you think of each toss as a stage, and we know that we have two choices here, two choices here, two choices here, which leads us to 2 cubed 8 choices. Okay, so that's you thinking in terms of a formula. What is a way that we could visualize this though? Because that might be necessary sometimes. Sometimes it's hard to think in terms of a formula. You want to be able to kind of see what you want to be doing. One way to actually do this is with a table. So the basic idea is you can double process with, should I say this in general? N outcomes being repeated. We can list all in a table where we alternate the outcomes as described. So you can construct a table and it's being repeated however many times you want. But here, you're going to alternate every n to the 0 rows. Then here, you're going to alternate every n to the 1 rows, every n to the 2 rows, etc. So for example, where the number of rows here are given by the multiplication. But now you might want to actually see what the actual individual possibilities are, you can fill in a table. So for example, with the 3 coin tosses, which should be a 3, we know that there are 2 possibilities. And we have the experiment repeated 3 times. Hence, what that means is I can write a table with 3 columns. I know there are a total of 8 total possibilities, so 1, 2, 3, 4, 5, 6, 7, 8. And so how would we fill out this table to make sure we're looking at every possible situation? Well, here there are 2 possibilities, so I'm going to alternate every 2 to the 0 rows. Then I'm going to alternate every 2 to the 1 rows. Then I'm going to alternate every 2 to the 2 rows. And I can stop there because I know that's only being repeated 3 times. So what does it mean to alternate every 2 to the 0 rows? Well, 2 to the 0 is 1, which means literally every other row I'm going to alternate the options. So start with heads, alternate to tails, heads, tails, heads, tails, heads, tails. Here I'm going to alternate every 2. Heads, heads, tails, tails, heads, heads, tails, tails. Here I'm going to alternate every 4. Heads, 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 tails, 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 tails. And it turns out by the time you fill in all the columns that you want, that would represent all the possibilities. So you can get heads on the first toss, heads on the second, heads on the third, tail on the first toss, heads on the second, heads on the third, etc. That's all the possibilities. You'll notice that there are 8 of them, that's the multiplication rule. But as for the actual arrangement, for you to visually see what you want, a table is a good way to go sometimes, especially if it's not going to be that large. I mean, 8 rows is really not that big for a table, so you could actually do that. So if someone were to ask you, what is the probability that when you toss these coins you get exactly 2 heads? All you're going to do now is you're going to count the rows that have exactly 2 H's in them. So that would be 1, 2, 3, 3 out of 8, right? Which, by the way, was the answer to the problem on the probability teaser page, right? So I could have just listed everything in the table, literally count what I wanted, and you'd see that 3 out of 8 is the probability of having 2 heads. Another way to do this, so this is the second way. The table is the second way. So sometimes you want to just see what's going on. A table is a nice way to see that. Another way is the tree diagram. Here, you visualize the outcomes are branches along a tree. So you have the singularity, right? The point where the Big Bang happened. This is where the start of the experiment. And it's going to branch off. And you can kind of imagine different stages here. So like, that's just the stage 1, that's the first toss, stage 2, that's the second toss, stage 3, that's the third toss. And so, okay, at the beginning of the experiment, what are the possible outcomes? You flip a coin, there are going to be 2 possible outcomes. So you literally draw 2 branches. You can get a heads or a tails. That commences stage 1. Finishes stage 1. Once you're here and you're about to start stage 2, this is now your new starting point. And what are the possibilities? Well, now there are 2 again. And if this was your starting point, you again have 2 possibilities. And then, if you were in this possibility, you would have 2 possibilities. This possibility would have 2 possibilities. This possibility would have 2 possibilities. This possibility would have 2 possibilities. And what you'll realize is that the number at end is equal total options. So you'll notice that there are 1, 2, 3, 4, 5, 6, 7, 8 things at the end, which means there are 8 total possible outcomes for this thing just by counting on that tree. So in the first stage, I can get heads or tails. In the second stage, if I got a heads, or I could get a heads or tails after that. In this, I would be able to get a heads or tails. Here, I'd be able to get a heads or tails. Heads, tails, heads, tails, heads, tails. So here, each arm represents one possibility. So like this one, H, 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 if you run along this arm, that's the possibility identified by the first row. Or I could have heads, then tails, then heads, and such a possibility is represented by this row. Or I could have the heads, then the tails, then the tail, or a tail, then a head, then a head, then a tail, then a tail, then a head, etc. Right? This is actually all of them. Right? So each arm here represents one possibility. These are all possible timelines. I mean, Thanos snapped in one of them, or he didn't in the other one. Right? There are 8 possible futures for this coin toss. Has anyone, you ever saw that show Community?
Yeah.
Remedial Chaos.
Huh?
The Remedial Chaos Theory episode, where they have like the different timelines and they're playing.
Yeah, when we were playing.
I love that show.
It ended too quickly.
What's it called?
Community. It's on Hulu. It's awesome. Anyway, they had this episode where it's like every time you tossed a die, a different timeline happened, and so that one episode played out a bunch of ways. I like it. Anyway, here each arm represents a possible outcome. And each, technically what we call these things are nodes is a common phrase for it from networking. Each node represents the start of a stage within an outcome. So again, here there are 8 possible ways for this situation to end up, and someone can ask you about, what's the probability of a certain kind of outcome happening? Like, what's the probability that I will only have one tail, right? So then you just simply count off the arms where there's only one T on it. So like this would be a possibility. This would be a possibility. This would be a possibility. In fact, that's the only possibility along that timeline, whereas this timeline will have 2 possibilities. So ultimately, again, you get 3 out of 8. There are 3 out of 8 ways that you could get exactly one tail. And you can literally just count off visually what's going on. So those are just some other nice ways to look at certain problems. If the possibilities are small enough, you can actually draw a picture of it. You can do this picture like in general, but sometimes, of course, there's so many possibilities and it gets ridiculous. You don't want to be there counting. But it's just an option that I think you guys should know about. And sometimes later when we're visualizing certain probability problems, I might draw a table or draw a tree diagram or something like that. Let's move on to probability. We'll be doing finite probability. Let's start with some definitions. A random experiment is a process whose outcome cannot be predetermined. With uncertainty. You flip a coin, you don't really know what's going to happen at the end. You can guess, and you can even be right with a guess, but you don't know, right? You can't really predict it, right? So if someone shuffles a card and you pick a random card out of the deck, you can't really know what card you're going to get. Sure, you can calculate chances of the kind of card you're going to get, but you don't know exactly. So whenever there's such a thing happening, and of course you realize in life, almost everything's a random experiment, you want to know about what are the chances of certain outcomes happening, which is what probability tries to do. Probability seeks to measure the likelihood of random outcomes in a random experiment. Let's talk about another definition. Now, this is important for a random, let me correct it, the sample space of a random experiment is the set of all possibilities, all possible outcomes of the experiment. Okay, so you find some way to represent in symbols all possible outcomes. You put all these symbols in a set. You say you've created a sample space for that experiment. The elements of the sample space are called sample points. And definition. An event. When we say an event happened, an event occurred, it is a subset of the sample space. Now, remember what subsets are. So you have a set that describes all the possibilities for some random experiment. Each thing in there, we call it a sample point. If I take a subset of the things in there, we say I've created an event. Right? So we're making this idea abstract. Okay? So, because that's how we're going to be able to do our math with it. So, what else do I want to talk about? We say the sample points are equally likely if they all have the same chance of occurring. And finite probability, the ones that what we'll be looking at, deal with finite sample spaces. There are experiments that we can conceive of that will have an infinite number of possible outcomes. We are only going to concern ourselves with a finite number of possible outcomes. So now, definition, let S be a sample space equally likely sample points. Let A be an event then the probability of A denoted P of A is, well, is given by this equation. This is how we are going to think of probability. Find a sample space that describes a random experiment. Figure out a subset of that we care about. We want to know what's the chances of that thing is going to happen. What we're going to do is we're going to measure the size of the subset that we care about and divide by the size of the sample space. This is defined to be the probability. So, for example, probability of getting H on a single coin toss. How you're going to want to start thinking about this is you let S be the set of, say, H and T. And here, your event A that you care about is getting H. So this means the probability of A getting heads is going to be the size of A divided by the size of S. Count how many things are in A. There's one thing in A. Count how many things are in S. There are two things in S. The probability is a half. Very easy example. So let's talk about process for finding probabilities. So the definition is going to tell us how we are going to want to find it. Like I said, one, you are going to create a sample space. And here is where you have to be creative. So it does need some creativity. For the most part, the kind of examples we'll do, you'll learn that the kind of problems we tend to lay them out a certain way. But what I mean by being creative, you want to envision what your set is going to look like. It's just going to be a set of symbols, random symbols. Is it going to be a set of sets? Is it going to be a set of tuples? Is it going to be a set of what? Right? You have to find a way to actually distinguish the possible outcomes. That can be very hard. Sometimes it's going to be very hard to actually represent that with people like the events. But situations like that, if they arise, I'll tell you how to deal with them on a case-by-case basis. One, you are going to find, so create a sample space S. Find the event in S that you care about. Maybe you have to find the event. What we want to do basically is, even if you don't find the event, at least find the size of it. You're going to find the the size of S and the size of A. Find the event A in S. Or probability of A is going to be the magnitude of A divided by the magnitude of S. So that's the basic process. The thing is, different examples will make step 1 more or less challenging, but step 1 is actually the most challenging part of the problem. You have to know, how am I thinking about this situation? Is order going to matter? Is order not going to matter? Do I want to think of it as just random a list of symbols, or a list of sets, or a list of tuples, or a list of something? But once you actually figure out how you want to think about it, step 1, the others tend to be a lot easier. You can just use your straight up counting techniques to finish off the rest of it. Anything else I want to say before I jump into some examples? Okay. Let's mention to you some axioms. At any given time, there are 3 things that we will consider to be true. They don't require proof, but you'll see that it actually fits very nicely with what we're saying here. 1. For any event A, probability of A is a real number, such that we'll always get a number between 0 and 1. So in this class, if anyone ever tells me, oh, the probability is 3, I'll know you have no idea what you're talking about. The probability will never be 3. It'll never be minus a half. It'll never be 17. The probability will always be a number between 0 and 1. So if you don't get a number between 0 and 1, it means you're thinking about something incorrectly, and you should know that you're thinking about something incorrectly. So that is what we're going to do. BTW. One way we can see this, by the way, we're setting up probability, is if you look at the probability of the entire sample space. In fact, that's going to be one of our axioms. It'll be, by definition, the size of S over the size of S, which gives you 1. So, also, look at the probability of the smallest subset you can create, which is the empty set. That's going to be the size of the empty set over the size of S, which is going to be 0 over the size of S, which is going to be 0. So, maximum, everything happening potentially, probability of 1, or any one thing in there happening, probability of 1, and the probability that none of the outcomes are going to happen is going to be 0. And these are 2 extremes, so we take the axiom that it has to be between one of these extremes. So technically an axiom is something that you don't have to prove, it's just something it makes sense to you in reality, so you just believe it. What I stated there is actually the second axiom. How you can think of this as the probability that some event in S will occur is 1. So you flip a coin, you define the sample space, heads or tails. As far as you're concerned, one of them has to happen. What is the probability you're going to get heads or tails? It's 1. I have to get either heads or tails, right? There's no other option, okay? So once you've defined all possible options, the probability that your event lives in that space is going to be 1. And here is why I needed that earlier definition. The probability of A1 union A2 union A3 union union AN is going to be equal to the probability of A1 plus the probability of A2 dot 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 plus the probability of AN not always. If A1, A2 dot 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 AN are disjoint. The probability of the union of disjoint events is going to be the sum of the probabilities. There's also something called, it's one of the rules that we're going to use all the time. We'll talk about it later. The law of disjunction, it's called. It says the probability of A union B is equal to the probability of A plus the probability of B minus the probability of the intersection. So that's a formula we know now. We will consider this to always be true. You can see why this would be true. Well, why? Probability of A or B is just going to be the size of A union B divided by the size of the sample space. By the definition, this is equal to, I actually asked you guys to find the size of the union before. It's going to be the size of A plus the size of B minus the size of A and B. By inclusion-exclusion principle. This is just a fraction that I can split up. Size of A over size of S, size of B over size of S, minus the size of A intersect B over the size of S. And that's just by algebra, or arithmetic I should say. And then by definition, this by definition is the probability of A, that by definition is the probability of B, and this by definition is the probability of A and B. So if I want to measure the probability of this or that happening, this equation is always going to be true. So find the probability of each individually happening, and then subtract the probability of both happening at the same time. And that will give you the probability of either or happening. The thing is, for disjoint events, remember, the intersection is empty, and so the probability here will be 0, and then I just get the sum of the probabilities. But this works in general, whether A or B are disjoint or not. So that's a nice thing to know. Examples now. I don't know how far I get into the examples anyway. Just drive another thing out. So, recall also, I told you a long time ago, that if you have a universal set, we can always think of that as a set union its complement. Like that. So here, in probability, our U is the sample space S. So, for any event A, the sample space can be thought of as that event union the complement of that event. And of course, A and A complement are disjoint. They have nothing in common. If you're inside the circle A, you can't also be outside the circle A. And this means that the probability of S happening is going to be exactly the same as the probability of A union A complement happening. we know that the probability of S is 1, that's by the axiom of probability, and we know the probability of the union of disjoint things is just the sum of the probability of those things, again by another axiom of probability. And this tells you how you can find something in terms of that thing not happening. So this means that the probability of A is 1 minus the probability of A complement. This is a very important equation. It is called the complement probability equation. Why? Because sometimes figuring out how something won't happen is going to be easier than figuring out how it will happen. So this is called the complement probability. Useful. In counting how many ways something would not happen. It's easier than counting the number of ways it will. Maybe I'll give you a quick example of that one. Example. You flip a coin 3 times. And what is the probability? You get at least 1 head. So that could be a question. Okay, now, you guys have probably seen this before, but at least 1 means 1 or more. Right, that's what this means. So basically this is asking for the probability of 1 head or 2 heads or 3 heads. Right? That's what this is asking. So now you start to have to think about, well, how many ways could I get 1? And how many ways could I get 2? And how many ways could I get 3? And do these overlap? And can I just add them? You'd have to go through that whole thought process, which here it's not going to be that bad, but just to emphasize to you how much easier it could be. Now, instead of thinking about these situations, think how many ways you would not get at least 1. Right? So this would mean you actually get none. That would mean you get all tails. And that would mean, how many ways can you get all tails? Well, there's literally only 1 way. Every single time you flip a coin, you get tails coming up. There's only 1 way here. Tails, tails, tails. The moment an 8 shows up, you're not in that situation anymore. So that's 1 way. So if A is at least 2 heads, at least 1 head, then the complement of that, the opposite of that, is all tails. And so I can find the probability of A by just taking 1 minus the probability of A complement. Now, I know that's going to be 1 minus the size of A complement over the size of the sample space. And we've already seen what the size of the sample space is. For this particular situation, it was 8. So that's going to be 1 minus 1 over 8. In other words, there's 7 out of 8 chances, 8 ways that you get at least 1 guess. Right? So rather than thinking about multiple situations, you can think about one situation. I had a bunch of examples today, but I think we'll continue next time. I'll just type them up so we move faster. So we'll stop there. This is the beginning. Yes.